So, welcome to the first session, masterclass session here. It's titled Let There Be Block. Let me first start with a quick check of the audience. So, who is stake pool operator? 1, 2, 3, almost everyone. Cool. Developers? Okay, also. Somehow active with governance like DREP? Okay. Anyone has seen already my presentation here in Dubai last year? That's half of the room. Okay, so that means I will not skip the first sessions. I will go through a little bit quicker. A last audience check. Please, everyone holds up his hand and takes it down as soon as he doesn't really won't be able to explain the next term. So Cardano, I assume everyone can explain something. Please, hands up, everyone. The next thing, blocks. Just keep the hands up and take it down as soon as you feel not confident anymore. Propagation. The next thing is a block header. The next thing is latency. Oh, quite good. Block header pipelining. Okay, good. That I will explain a little bit. Peer sharing is quite new. And blocks from the future. Okay. So I will mainly talk about networks here, but then explain what it has to do or where it relates to governance, that new thing that we have in our network. This here is a network. It's the public transportation network of Las Vegas. So it has lines, stations, trains, and passengers. And how it relates to our network, we have connections, nodes, blocks, and transactions. So in this session, we will focus mainly on the blocks. So think about these are the trains. And when it is about trying to understand how it works and where we can improve, then, and especially now in governance, we may want more blocks or faster or larger blocks. So this basically is then governance, and people will come up with, especially developers or dApps and so on, and demand from our infrastructure layer, so the SPOs running the infrastructure layer, demand more of this. And yeah, this could be simple claims like, let's double the block size. And then either we have a decision like, yeah, let's do it, or we demand, please prove that we actually can double the block size. Just making an example, not saying we should do it right now. So this is where monitoring comes into place. The challenge here is at one side, monitor for operational resilience, and the next one is for governance. So like capturing data that is a fact base for research, for insights, for proofs that can lead to a better opinion, individual opinion, so not like pre-paired opinions that everyone has to believe in, but more like raw data or data sets that is open and everyone can look at it, form his opinion, and then participate on a solid level in governance. So the benefits on the operational resilience side is reliability, and on the governance side, we aim for improvements. So like larger, faster, more capacity, or even more reliable. The session is split over, will come in a couple of parts. So the first part is more what actually the challenges are. Then I will explain a little bit what we actually measure. And in the last part, I will show you a little bit what the benefits or what the potential outcomes could look like. So this is what you, I believe, know very well. There's slot by slot in a timeline, and you have some of these slots are filled. When one of your pool is an elected slot leader, then he will produce a block. What we look here right now is the gap between the slots, because this is the time that we have to propagate the blocks around the globe. And if I count these blocks, these empty slots between the blocks, then for example here, from the first to the second block, we have a gap of 6 slots. So I count up here by +1 in this chart. The next one is a +20, so I count up +1 on the position 20. And if I do this for a whole epoch, now a question, how would you expect the distribution, the resulting distribution looks like? Is it like this? So like mostly every 20 seconds? Or is it like this? Or is it like this? So who is for the red one? For the blue one? Okay, you have seen my session last year. It looks like this. This is a distribution from a long time ago. The blue ones are blocks actually adopted. The yellow ones are slot battles, so they cannot be adopted. There's always one block winning, the other one losing. And the orange ones was hate battles back then. This was before header pipelining. So after header pipelining, so the orange ones actually, I filled them up manually. This was never adopted blocks. They was lost in battles. And after header pipelining, it looked like this. So I had to fill up way less, an improvement already. But this improvement came from research and engineering from IOG side. So they looked into this data. They had some monitoring in place. We was more like, hey, why did you, other pool, not propagate your block faster? But not really. We had our own perspective on the why my block was not adopted or run in a hate battle. So the block production challenges are: we aim for a timely propagation, for a solid topology, how this topology looks or evolves. It was previously like a static, everyone connects to IOG nodes, then someone used a topology updater or did some static configuration with other pools. And now we have P2P. The thing on the monitoring here is also to understand not only block propagation, but also how these peering connections evolve and live from a node that starts up stateless and tries to find the best connections to the network. So the goal is also we want to minimize these forks, especially hate battles. Slot battles, we cannot avoid it, so that's by design. Also, the monitoring is about computation. So you will see later here that we measure 4 steps, and the first 3 steps are all about network. The last step is local validation, and that's all about your computation power or whatever may causes a delay. Proper configuration, of course, this means you may have a setup that works well, but then the situation out there in the network changes, like you get a lot more incoming connections, and you start then seeing that a certain pool starts having more and more delays on his blocks if you monitor it well. The problem here, or the challenge here, is you produce your blocks and they are here. So you cannot really monitor that they are propagated. So you miss how your blocks are, your own blocks are perceived from the network. Let me come back later to this. So monitoring, yeah. Another part 2 now about the network layers. This is where you all operate your pools. So these are like in a ISO-OSI layer. The upper layer, it is similar or aligned or tries to design to show this like an ISO-OSI layer. And you have the application like Cardano node, the software, the hardware, if you run hardware. This is what you monitor, ideally, hopefully, and only you can monitor it. So I cannot look into your CPU usage, disk space, and so on. So everyone monitors it for his own. There's the underlying layers, so like the global network, and this is where you have a challenge to understand how your blocks, how your contribution to the blockchain is perceived on the global network. Because there is also no single monitor, no single value that you monitor. It is like thousands of other nodes around the globe. And they may see it very fast if they are close by to your infrastructure, but they potentially also with quite some delay if they are on the other side of the globe. So in between, we have here IPv4, IPv6 networks. So a lot of the monitoring we do is based on this layer. This is locally you, and this is this global network. Again, here, this is what I already said. You monitor your own resources, and this open block perf monitoring aims aims to measure and capture how others experience you, the global state. So also independently of only you, but more like look at all the pools and all the blocks and all the propagated data, just from a general perspective. It's block propagation, but also more. So it is also potentially transactions, mempools, topologies, and other unusual patterns. I will bring some examples now. For example, also it is not monitoring right now or the last 5 minutes, but capturing a certain value, a certain calculated indicator per epoch, and then putting all these values in a time row, and then you see a trend like we are improving or it's getting worse. Here, this is now a short animation in order to give you an idea how block propagation works at all. So what we do here is we have nodes like this is your producer, this is your relay, very close, and this is another peer where you want to have your block reached or adopted. So first, let's start with the very first step that is here. What we have is a distance, usually from your producer to your relay, it's very close. And then here we measure time. And the first thing you do is you produce a block in your scheduled slot. Then you announce a header, and please note here the colors. So this is why I show it. The remote node is basically then saying, okay, you announced me a header. I don't have it locally, so it's sending back, please send it to me. This is also very important to understand. The design of the Cardano network is very conservative. So it's always a ball game between two nodes, and the next step can only happen when the other side, when the remote side reacted accordingly. I cannot decide to connect to you and then flood you with information. This is not going to work. I can decide to connect to you. So you announce headers to me. I send you a request. Please serve me the block. You send me the block. So this is permanently a thing. And yeah, this is what we need to also understand here. So what happens is the block is fetched, and then the local adoption here happens. So you have this one-time purple thing that happens only on your producer. Then you have 3 steps that happen in our network, and the last, the blue one, on your local node. So the next hop is very similar, just without the block production. It announces the header, sends the fetch request, and serves the body. As the distance is larger, especially the body serving takes longer. Keep in mind, we have block sizes up to 88 kilobytes, and the TCP/IP frame is only 1,400 bytes, so 1.4 kilobytes. A TCP/IP acknowledge window is 1020 fragments. So by sending a whole block size, it is not only the latency from your node to the other one, so it takes 200 milliseconds to send a TCP/IP fragment from Europe to Japan, but after 10 such fragments, the remote node needs to send an acknowledge, okay, I have received it, please go on. So this means this is a back and forth of packets, and they add up as latency. So if you have 200 milliseconds of latency from your node to the other side of the network, to the globe, by sending a large block, this can quickly add up to more than 1 second. And 1 second, 1 slot, troubles, hate battles. So Yep.
Without question between.
Yeah.
One question, the new block height should be, I think, after the error, right? Because we have to first do the local validation before you announce the block height.
This is how it was before header pipelining.
Okay.
So header pipelining basically broke the black arrow from here. So this black arrow first was here, and with header pipelining we save it this one. The thing is, it could be even better, theoretically. We could already announce the header, so as soon as the header was announced here, this relay could already announce it here. The problem is that is very quick because the header fits into one TCP/IP packet, but then the remote side will send back a fetch request for the body, but the the announcer of the header still he himself has not the body yet, so it will not save time. So this is why header pipelining is limited, but as you have seen in the previous two charts, it already helped a lot. So like it was very useful already. So what I wanted to show you here and why these colors is these arrows here with the colors, you can also visualize it like this. Or let's remove the arrows, it's only like this. And if you, so this is basically the experience of a new block from two different nodes. It's the same block, but it's from two different nodes in different locations in the global network. And if we do this measurement on many nodes on the network, then it looks like this. Of course, if we now go back to the presentation, the topologies here, I go through quickly. This is how we started with everyone connects to IOG. And this is more like decentralized with some own peerings, a little bit of topology updater. The P2P with autonomous decision making of every node is what we actually want. And then when we have an autonomous decision making, it's the most difficult thing to actually monitor it or to get an understanding how it actually works and how it evolves over time. With dynamic P2P, which is this module that should help us to achieve this, we have a concept of cold, warm, and hot lists of potential peers, and the selection of these peers is stake weighted. It has in a built-in random change, so it does not like end up in a fixed situation, but it permanently drops a random amount of existing peers by hoping that the next randomly selected will be even better. So it is a permanent change. This means also if your node works well and your P2P module feels fine, it will permanently drop a few and try to find even better ones. It's a good thing for, let's say, quite small pools or new evolving pools to get into the network at all. As for now, this random selection is only happening from on-chain data, so only the relay nodes that every stake pool registers with his pool certificate on-chain is basically the source for this random selection. Later on, it should also come from peer sharing. Now on this cold, warm, and hot lists, every node starts, when you restart it, starts stateless. So it does not remember which connection it had in the previous runtime. The cold list is just a random stake weighted pick, a list of random stake weighted picks. There is no connection. So it's only basically picking some IP addresses from a huge list of 5,000-6,000 registered nodes or relay nodes, but it does not connect anything. So that is where warm comes in. So in the warm pool, the node tries to establish a TCP/IP connection to these remote peers and also keep it up. But then the thing is, it does not talk. This is hot. So on the hot list, it starts talking mini protocols like, here's a header, please send it to me, or this is a new transaction, and so on. So this is what you need to understand. And then usually, or the default values are that there should be in the default node config file, the module should pick 150 random IP addresses, establish 50 connections, and then start talking with 20 of them. And then from these 20, after an hour of runtime, he looks which one was the most useful. So it has a ranking, which one announced headers or served blocks. And the worst ones are dropped and replaced by new from the warm list. So this is basically how it permanently lives. As long as you keep the node up and running, it permanently tries to keep the best and to replace the worst. This then, on a global map, it looks like this. So you have here a node on the US East Coast, and it starts establishing this connection and starting also talking mini protocols. And on another node, for example, here in Dubai, it would then look like this. Now you can imagine if you overlay here thousands of relay, how this network would look like. Here, a little bit more in numbers. This is the same part what I showed you in the previous slide. Just now do some little math. Assume we have 3,000 relay nodes in the network. This means we have 150,000 TCP/IP sessions permanently established, and every block is basically passing or potentially passed over 60,000 mini protocol active sessions. All of this, ideally, within 1 second, one slot. So, and all of this is happening right now, permanently, for every block. What we try to do with this project is to monitor data to understand how this works. This is where I now want to, actually the project is not so new. Some operators already participate for 1 or 2 years to this project with their own perspective, with their own view. It was first my private project, then it was brought to the foundation, to the Cardano Foundation, as I recognized, okay, this project is becoming larger and larger, and in the foundation, as a neutral, non-profit entity, it's the right place to be hosted. So Open Block Perf, what it does is, if you run your Cardano node, then it writes log files. The Open Block Perf module is basically plugging in there, and it still writes your log files. So you don't lose anything, but it intercepts and it looks at certain signals, especially timely precision signals at millisecond level. And what we measure or what we capture is the time from the theoretical slot start, like millisecond 000 at the theoretical slot start time, until the new header was announced. Remember the 4 colors. The fetch request was sent, the body was downloaded, and the local adoption was completed. And in a telemetry aggregation network globally, this data is served into a large database that is hosted partly on my side now, but then on the foundation side. And the concept is you contribute with your view, and the benefit as a stakeholder operator is you got back a global insight or the views from others about your data. So it's a win-win. So you contribute, you get back something, especially because if many contribute to this, so especially, and what I want to invite here, it will be super important to also have more coverage from the US side and Asia side to contribute to this, because this has a huge impact on the global propagation. Here now some examples how this looks like. If you remember these bars that was from bottom up, now they are switched by 90 degrees. So on the top here, you see a timeline with basically all the slot numbers. And here you see a state from some months ago. And you see here a single node from Nairobi, Africa, reporting his experience of the block number 8033. It was a larger block. And you see here, if I click here, that it took him 221 milliseconds to first hear about this new header. Then the fetch request was super fast. The download took like half a second, and the local adoption was like this. and the next block then came maybe from somewhere else. It took him a little bit longer, and so on. So if we go back now, there's another example. And now if I load it, first in the first example, I consciously only showed you one reporting relay to get a first understanding of these charts. What we have here is hundreds of nodes reporting the experience of this block. So in this one slot and this one block, in this case here, it was a slot battle. So you see here like an overlay. The block was received 2 times, or 2 blocks was received at different, slightly different timings. And I can also show you here on this how they actually appeared or globally propagated. So this here was the winning block. In comparison, the losing block had the lower VRF hash. And so, sorry, the other one was the losing block. It propagated a little bit, but then it didn't end up as the winning one, and this one was the winner. So this one propagated from here. If I go back to the next one, here, this is an example of a hate battle. So what you see here is that the first that we have here the block 112, and here also 112. So this one did not build on this one, but on the preceding one. Classical hate battle. Why? Because this block was only announced here. So this one could not ever know about. So this is how a hate battle looks like, or how a hate battle is created. You can see this one. This is a late empty block, so also causing a hate battle. What is interesting here is that this block here was produced with, let's say, 1/3 or half fillet, so 33 kilobytes, but this one had 0 kilobytes and still took him way longer. So this is like an indicator that this is not really a block propagation issue, but more like a local production issue on this node, because he didn't even manage to get transactions into his mempool. And then he created somehow a block, but did not even receive transactions. Could also be that if this is a repeating thing, we could see a pool producing permanently empty blocks because he does not receive any transactions. So like a wrong peering setup on his side. Another example, this is now a block from the future. So how does a block from the future look like? The slot for this block is this one here, but the block appeared way earlier for all the nodes, reporting nodes in the network. So how is this possible? If the producer local system time is ahead, then he assumes or he sees the time has come, he produces a block, announces it, and it gets announced here, and then also the fetch request happens, the download happens. Back then, so here still in August, we had node versions previous to node version 9 that had a little bug in it, and so the bug, you see it here in the blue line. So when a node received a block from the future, so from his own perspective, this is a block for a slot that has not yet come, then he goes in a wait state. The problem is he remains in this wait state even after the slot has come. And he remains in this wait state until the next block is announced, which means, okay, we have a hate battle. So this was a problem. Here in a less so there is also then there is an issue that if the time of the producer is only very minimal, so not like a full second, but more like between 150 and 200 milliseconds too early, then it depends on the local propagation time. If the relay receiving it receives it too early, gets stuck, or in time and adopts it locally. And then you have basically a fragmentation of the global network. Half of the network has it adopted, half of the network not, which is not so So let's say it's not critical, but it's really not ideal. And then it depends on the next producer. If that producer has received it in time and adopted, then it continues with it. If not, then it gives a rollback. I remember Ola had a very special case in this one. I actually already have it here in an example, but in order to save some time, I excluded it because it's also a little bit difficult to explain what happened there. This here is also interesting because the first block, you see here still 2 blocks with the same number, but the first one perfectly propagated in time and everyone received it, except the producer of the next slot. This one had a receiving problem. He did not learn about the first producer and produced his block not on top of the previous one, but on the second previous one. And actually, he also had obviously some problems to propagate them. So he was basically low on resources or whatever it is. This is also a case where we can see a hate battle. Long adoption times. This is an example. What we see here is, okay, why basically the first one, but also the second one and the next one. Okay, I limit it here. Basically, in this phase here, out of, I don't know why, or we don't know why, they all took longer. So actually here we know why, because if you look at the time, this is local UAE time, you see somehow it's minute 44 and some seconds, 50 and some seconds. This is the epoch boundary. So the nodes have to do a lot of things, and in this time, all the nodes, even if you have super Xeon, what else, computing power, the node is, the Haskell implementation is limited for quite some security reasons in single core computation. So it cannot do everything in parallel, even if it would be obvious, like a stake snapshot could easily run in a separate thread from block production of the current block, but this is not the case right now. There's a current example, let's say from this summer. Who remembers the TX spam, not denial of service, but issue? So if you look at this, this is very interesting now. I think this is really very interesting because here you see the last 2 blocks before the attack started. So everything fine, even there was a slot battle randomly, all fine. And then our colleague, the attacker, started doing something. And the first block looked like this, the second block looked like this, the next block, and this went on for 12 hours, or many hours. And the thing here is the stake pool operators looked at their own local monitoring values, and the node exposes this CDF 1, 3, and 5 counters, but they count only the first 3 steps, so the network step. It does not count in the local adoption time. And you see here the blue bar, the local adoption time, is the most affected because the transaction was a spamming with recursive calls of scripts. So the execution, the whole adoption was not on the network side, but on the local adoption side. And the SPOs themselves, from the exposed metrics, could not see it. They could only see it if they would have gone into their log files and looked for these 4 propagation steps and then count the milliseconds or the time delta between in order to recognize, okay, the problem we have here is on the local adoption and not network propagation. So when this happened, many operators even tried, for example, to restart their nodes, which made it even worse. My point here is it is important to capture this data and then do also give an understanding. It's not only about, not only you, but all have the same thing. So you can already skip to look at, is something blocking my resources or else? It's a general problem. And the next thing is to visualize it. So not only capture telemetry data in numbers into a large database, but also visualization. And so the last chart I have here, the last chart that I can show you here, because this was all some specific examples from the past. And basically the system is already running in a real-time thing. So these are the blocks from the last 5 minutes. And this here, these 3 blocks was just produced. So this was a hate battle just 10 seconds ago. So it looked like this. Let me show. It appeared here and it didn't make it everywhere. So this is actually a very good example. Randomly right now happened. We captured here a slot battle, but only because many contributed to this view. If the node who reported this here would not already participate in Open Block Perf, we would not have seen it now, even if it happened. So this basically, this is why I say it would be important to have many operators from different places around the world to contribute to this project. Now, as a last part here, what can be made out of it? You already have seen these Gantt diagrams, all the examples so far, but there are other charts and views we can capture. For example, here, this is a long trend chart, and basically we look on how many delayed blocks per day we had. And the S1 is 1 second, so a block that arrived with 1 second of delay and more is the green line. And if we count it then with 3 seconds, 2 seconds or 3 seconds and more, then of course they become less. And if we put this all in a line, then we see, okay, we had a growing number of delayed blocks, especially in the 1 second area. So if it is a delayed block by 1 slot, then it is a potential hate battle trigger. If it is more than 3 seconds, then it goes into this area where we say the Ouroboros security assumptions are on a limit of the security budget, on the time budget. So the yellow and especially the red indicator is where it becomes security-wise relevant. The green one here is where it becomes an annoying thing for the operator losing a block in his hate battle. What we also can look like is we don't look at registered or somehow known relay nodes with IP addresses, but we actually count where blocks come from. So as we get the metrics in where headers was announced and blocks was served, by counting only these nodes who actually announce a header or a block first, so actively contribute to the extension of the blockchain itself, we can have a different charting or understanding of the network. So it is like really the active contributing network. Let me say I have some physical resources in a data center in the north of Italy. I could spin up like 50 nodes, potentially also let them appear behind 200 IP addresses for the same nodes, and it would look like Italy has 10 times his current relay nodes. But actually it's not really serving or not useful. So they don't have the stake behind of it. They will not really contribute. And by actually looking only on the real contributions, it could look like this. Keep in mind, this is a chart from more than a year ago. Here also to point out how different this can be, look here we looked at countries. So IP addresses resolved to countries, and here we look at ASN numbers. So you see in the x-axis the names of the data center providers. The blue line is counting known IP addresses. The red line is where blocks actually come from. So you see, for example, that Amazon has quite some nodes, but it's on the second place on the blue bars. But it has a lot of stake behind of it. So a lot of blocks come from there. So if we look at our network, then we can look at just known IP addresses But again, I personally would prefer and always recommend to look at where blocks come from, because actually this is what defines our network and our blockchain. We also can look into node versions. This is more like, this is not on-chain data. This is more like every node participating also let us know which node version is operated. So if we look here on the left side with all a light blue, this was like 100% of the nodes run node version 1.35.3 back in like 2 years ago. And then there was a new software release, and basically here there was a new software release. It was then 1.35.4, and operators started implementing it over time. Someone did it on Friday, the other on Saturday, and so on. And then here and here it went then a little bit faster. So what we see here is basically a history on how all the pool operators upgraded their network, their nodes. They're contributing nodes. Note, this is not a full network view. We can never, nothing here is a 100% view of the network. It's always only the contributors and their perspective to the network. What we see here on the purple is, this was the Chang hard fork. So node version 9. And what we see here is at 85%, we had a hard fork, and this is not that they upgraded, but this is a 100% because this 15% filed off tip. They never upgraded. So also interesting. This here, if you remember the 4 colors in the bars, and if I count now all the blocks for 5 epochs and just look at the time, how long it took to announce the header, then I have a variation. I can draw a variation, and I see 7% or close to 7% of the blocks are announced at around 250, 200 milliseconds. And then if I extend it to the 4 steps, so you see the 4 bars colors here, then it's quite logical that the red, green, and blue is more on the right side because it can only happen after the header announcement. But this is basically a variation of the global situation, how all the blocks, so 21,000 blocks per epoch for 5 epochs, are perceived and received in the network. So it's quite good here to see that this works very well. The interesting thing is now that if you as a pool operator contribute to this view here, then you could get back a comparison of this total average values compared to your only own relays. So these are my relays in north of Italy, and as you see, they are more on the left side. It's a good sign. If one of these 4 lines, the dotted lines, will be more on the right side than the average of the global network, then you see, okay, there is some room to improve for me. So that's actually a direct benefit that you can get by contributing data. But there is much more. Here, for example, we monitor or we visualize the global perceived propagation times for one producer, and over time, so from September to November of last year. This was when P2P peer selection became a thing, and this proc producer got a lot of connections because a lot of stake. He had his systems running always with the same nodes. Everything was fine, but he got more connections. He actually did not look at the number of connections. And what we noticed here is that the propagation of his blocks went above 1 second, generally. So like, not always, but potentially he more and more run into hate battles. And by monitoring this, he himself produced his blocks in time, but he could not really see that they was perceived too late afterwards. This here is a similar chart, and this is where we reached out as a foundation to this producer, helped him to look at his data, and proposed him some improvement things. He implemented a few of them, and as you see, after we did this, after he implemented, we don't ever know exactly what he did, but we suggested him a couple of things, and he was actually able to improve the propagation time for his blocks by a lot. Now, as a last thing, what I want you to show is Gini index. I assume many know what it is, and usually it is connected or related to wealth distribution. It is calculated like this. If you have 10 participants in what you look at, if you have 4 participants in a system that you try to calculate the Gini index, and they have all the same weight, like 10, 10, and 10, then you have an ideal Gini index of 0, and the calculation looks like this. So if the distribution is not so equal, then the Gini index goes down. It is 0.6 here, and it is calculated like this. So this is only to show you how a Gini index is calculated. And if I do this by countries in our network where blocks come from, then this is our current distribution. The next thing is if I do this for the IP addresses on a geolocation or also on a network data center location, I get some numbers like the blue bars before. And if I do this epoch by epoch and calculate the Gini coefficient, then I get numbers. And the last thing is, if I put these numbers in a long line for the last 2 years, then it looks like this. So this is, in this room, you all see this the first time, so nobody has seen this before. This is the last 2 year decentralization of the Cardano mainnet network. So it is at around 0.75. Remember, 1 is bad, 0 is good. So we are not that good, but it is acceptable, especially compared to by far most other networks, blockchain networks. And the good thing is on the end, so in the last half year, you see a steady or a slow but steady trend towards the better. So P2P so far did not cause gravity hotspotting that potentially could be a risk, because stakeholder operators may see, okay, my blocks arrive late, so I'm too far away from the most other nodes. So my decision will be I stop the nodes where I currently run it and go there where everyone else is. That's a risk for centralization. So far we don't see it. So far it looks good, but there are also some more ideas to make this even better based on the monitoring data we capture. Last thing here, remember this was a slide in the very beginning, and what it is, what my main message for this presentation is, the SPOs operate and monitor the network. With Open Block Perf, we can make this aggregated data a common good, and then research, engineering, and also governance can use it. So basically, we on the infrastructure layer capture and monitor ourselves, but also provide it to the governance colleagues, the DREPs, and the upper layers, but also the lower layers, the research and engineering. I can tell you they are very much interested in this data. And the idea here is to make this data accessible, not as full raw data. For example, like exposing a list of all the public IP addresses and ports is not useful, or is like too much information from a security perspective. But there will be somehow permissioned access, so you can request the foundation to access this data. Why? The permissioned thing is because it should come with a scope. So if someone wants to look at this data, he should present a scope. So for example, I want to look into a parameter change proposal because I think we can improve something. This scope comes with a demand from the foundation side that there will be a deliverable. So the access to this data comes with the demand that what you create as a finding is then also published. We don't want that someone gets free access to open data and then looks only on his own benefit. So what we want to do is, and this is why it is permissioned, but then it is really then open to research for example, the next session here with Sarouche, his work is based on data coming from this system or from this concept system here already. And then engineering also can refine the models. So far in the history of Cardano, because nothing existed before the mainnet was here, there was all assumptions. Now we have actual data, so we can refine the models for future development, not based only on assumptions, but really on facts. And then for governance, of course, it's also a thing that more people can look into data, form their own opinion, and then participate in governance with a solid opinion and not a feeling like, this sounds good, this guy is not so trustable. I don't think that's a good base for good governance. This was it. Thank you. So let me quickly check how is the time. Yeah, good in time. If there are some questions.
Yeah, thanks for the presentation. I have two questions actually. First one is, how many pools do you currently have that use Blockper?
The thing is, 2 years ago I started with like 10 colleagues from thing, and then it was like an all-time high of like 150, 170 pools. And after some hard forks, I currently we are around 100 nodes around the globe. But as you have seen here on the just to emphasize it, if we look at some propagation time here, is it loading? So this was a delayed block. So you see here that it does not all are green, but what you see here is that the locations of the dots is the location of the reporting nodes. And so it will be really useful to have, let's say, Central Europe is very well covered, but every node that operates outside of this will be very welcome in this system. It will be very open, as I showed in this thing where I explained where Blockperf plugs in. Currently it is a script. It will be now be released as a binary with release versions, and it really plugs in then into the logging system. It may also comes with an option for the operator to log more, capture data, but then write out to log files only the things that are relevant for the operator itself. So we have a lot of ideas here. Yeah.
And any SPO can join this currently?
Yes. So the thing is, there are currently two versions of this. The first version is still the very old one that I run. That was completely permissionless, so everyone could just start using it. It is also integrated in CN tools, but there's also a standalone script version to easily run it. The only thing that is required is this tool needs to know where your log files are, and there needs to be 2 or 3 tracers enabled in order to have the data in the log files. That's quite easy, and it is completely permissionless. So it only sends data, and you don't need to authenticate. A second version is running. It is based on a Python script already, and it comes with a MQTT telemetry network. So MQTT messaging. And there to get the message into this, so submitted from you into this global network, you need a certificate. The idea was to implement it with CIP22, so the SPO authenticate himself that he is actually the owner of this pool. He gets a certificate. Right now, I work on a version 3 already with an improvement, and it should be really released in the next couple of weeks or months. And the idea is always that you can run it standalone based just on the log files. But ideally, we also have some integration in scripts. Maybe also Martin can provide some support to have it easily integrated on the nodes operated by his scripts. And then the aggregation is a global network with distributed nodes where we just capture all this telemetry. And that is a lot. Think about for every block we get like several hundreds of nodes. Right now I can tell you the database I have for the last 2.5 years is currently at 190 gigabytes of data. It is not fully optimized, so that was why it was version 2. Version 1, version 2 is already quite more relational. Version 3, I have even more ideas to improve it a little bit more. For example, one idea here is that we put watchdogs on this database. So like post-processing, post-operating watchdogs that look at very specific patterns. It could be like all the blocks with more than a certain amount of memory units or CPU execution units, and then just flag these blocks, nothing else. And then after a month, we can quickly select, give me all blocks with a lot of execution units. And then we look at propagation times or what it means. Or another indicator, like all the blocks coming from Asia. Whatever it is, this can be very, very specific watchdogs. It can also be alerting watchdogs, like no blocks for 5 minutes or a special situation where something happened, and this watchdog is running all the time. It does not send out any alerts, but after 2 years, if something very special happens that we absolutely don't want, then a Telegram channel or something where people are in, get notifications, look, you all have to look at it, not only 2 or 3 people from IOG. Not saying that was bad, but it was like the situation so far. Okay, other question?
I'm running the open versions, and I'm just mainly running that on my block producer. Should I be running that on all the relays as well to get better data to the network?
Yeah, good question. Very important. I never wanted, or really, it is not supposed to run this on the block producer itself. So this monitoring here is about the global network in between relays. So we don't monitor the situation between your relay and the block producer, also because it is a little bit special. The producing node already knows the block, and so the propagation between a producer and his relay time-wise is different than between the hops in the global relay network. So we specifically look at all the nodes, or all the hops and the propagation between the global network. We also, for security reasons, prefer to not have our system or software operated on the node where the keys are, so the producing keys, just on the relay nodes. And,
okay.
And from there, they submit. As a stakeable operator, you can run this on one relay or on all relays or on a certain amount of...
Does it give better data for the network if we run it on all the relays?
For the network, it depends. If you run it then on different systems or on different locations, then it's a benefit. If they are on the same data center and in the same TCP/IP subnet, then it doesn't really help. For you, it helps you to understand if both relays perform the same way. Actually, I can tell you this is something that I do for like not only on blockchains, but for a long time already, in order to understand if a certain setting configuration actually helps. I just run 2 systems in parallel with as same as possible with just one parameter changed. And then I look at the monitoring data and I see how much it improved or even made it worse.
Okay.
So when you participate with more nodes and you are not sure if you can improve something, then change it at one of your nodes, look at the monitored data, how it is perceived on the global network, and then you understand if it actually is a good decision for you or not.
Okay, and one more quick question. Do we have any data on how much system resources this uses when we're using it on the network?
It is minimal, but the good thing is, as it is an external module, just passing the log lines, it runs completely on a separate node, thread. So it is completely not affecting this single thread of the node, at least as you have more than 2 or 3 CPU cores. It has practically 0 impact.
Okay.
So it's very lightweight, very easy, and just...
And it can go in parallel, so it doesn't matter.
Easily,
okay.
No problem. Yeah. Sorry, there is a very strict timeline. If there are more questions, feel free to reach out to me, but we really need to end the session at the end of the hour. Thank you very much.